Okay, so we begin today by, well, so today the plan is to end, if I can, the part of this chapter, the part of this course on abstract vector spaces. So which means we will get to, like determinants and so on from either this class or the next class. Before that, I want to remind you of a couple of things because we will use them today. So first of all, we had a vector space V with a basis, ordered basis B, which is V1, V2, Vn. It's a finite dimensional vector space. From that, we obtained a dual space is also finite dimensional, and it has the same dimension. And then there was something called, let me call it V prime, which is something, I guess I'll call it phi 1, phi 2, phi n. And each phi I is an element of V star, of course. And its phi I maps Vj to delta ij. Delta ij means it's 1 if I equals j and 0 otherwise. Okay, so that's the thing. This is called the dual basis, right? This is called the dual basis to B, to this basis B. And one of the homework problems was that, of course, the dual basis is a basis of V star if B is a basis of V. Okay, so okay, great. That was that. And then we talked about, or we did not talk about, I guess, double duals. Let me check. No, we did not. So before we talk about double duals, we talked about transposes, right? So the idea was take any two vector spaces and any linear map. Then there exists a linear map called T star or T transpose, really. Maybe I should just call it T transpose. Well, look, the star looks nice when you have star and star here, so I guess we'll call it star. Sending the map phi in W star to phi compose T or T star phi. Right? Okay, and so that is that, and that map is linear. This T star is linear. It is called the adjoint of T or the transpose of T, and so you have to check that it's in V star, and that is not hard to check. Okay, so the point that I want to now make is the following. Okay, so suppose I have such a map T from V to W, and I have ordered bases. So now, of course, we know that a matrix is just a linear transformation together with a choice of ordered bases, right? So suppose I have a map T from V to W, and I have a basis VV and VW. Okay? Then all of this together means that I can look at the matrix of T with respect to VW and then VV, and let's call this matrix A. Similarly, I can look at the dual of this picture. So then I would have T star going from W star to V star, right? And then I would have and then similarly for W star, I would have the dual basis. Let me call this B prime W. Oops, this is not writing very well. B prime W and B prime V. Dual basis. And so I can also ask the same question. What is T star, the matrix of T star with respect to? Now T star goes from W star to V star. So first I have to write B prime V star or B prime V. Let's call it B. Let's call it BV star. B prime V star and B prime W star. I'll forget the primes. And then B prime VW star. Right, so is it okay? Can you write down this matrix? Is it related to A in some way? And of course, you can guess that the answer is yes, it's related, and the answer is yes, it is exactly the transpose of this matrix. Okay? So the idea is we will actually prove that. We'll prove that the matrix of T star with respect to the dual bases is the transpose of the matrix of T with respect to the basis. So we will prove that. But for that, I actually need to write down what is the double dual. Okay, so from a vector space V, I get to the dual space, then I get to the dual space of the dual space. So we will need that, and so we are getting there slowly. Okay, and so that's the idea of today's lecture. I want to talk about I want to continue with dual spaces, and before I talk about this thing, so this is today. Maybe I'll write this down in red or blue or something. Okay, so we are going to see this today. But before I do that, before I tell you about the transpose map with respect to basis, I need to talk about a few more things. I need to talk about the double dual. So before we do that, in fact, let's finish a few more topics in dual spaces, namely the Perp-space. You can define, so remember what the Perp, I'll say that, and then we will get to double duals, and then we will get to this one. So let's start with Perp-spaces. Okay, so what is a Perp-space? So remember, so let me just call it Perp-space. So remember, in an inner product space, you know what a Perp-space is. I think, okay, do I want to start with this? Yes. And I want to say, let's recall. Yes. So recall, in an inner product space, let's say Rn, in fact. Right? And W is a subspace of V, or even S is, let's say W is a subspace of V. We define W perp to be the set of all, let's say V in V, V in Rn. Okay, fine, V in V. So V is Rn, so I think this is V in V, such that V and the inner product with W, which is the same as saying V transpose W, if you will, is 0. Actually, 0 the scalar, so it's like. Okay? That's what is the Perp space. Now, we of course don't have an inner product over a general field or anything like that. But we do have this. What was this? Remember, this is an element. This is a row vector, and we know how row vectors act on column vectors. They act on it and send them to scalars. They are linear functionals. So V transpose is the same as saying this equals phi of V transpose, which is V star. And so really, it's just in V here, I could have just said V transpose in V transpose in V star, so that V transpose of W is 0. And that's exactly what the Perp space is. So in definition, and this works over a general field, you don't need an inner product. So given, let's say this W contained in V vector spaces over F, over any field, the Perp space to define W perp to V. So this is now going to be a subset not of V, as we say here, but it's going to be V transpose in V star. So it's going to be, let's say, phi in V star, such that phi of the entire W is 0. And as I said, this is in V star. Okay, and then of course the obvious claim is that this is a subspace and so on and so forth. Right. Okay, now do I want to say anything about the restriction map? No, really. Okay, no, so there's a theorem here to be said. Theorem. So now consider the following, right? So take any linear functional in V, right? Then clearly, first of all, this is a subspace of V. That's not hard to prove. So W perp is a subspace of V star, sorry. But now here is the more interesting point. If you have any linear functional of V star, then it's a function from V to the scalars. I can restrict it to W, and it will be a linear function from W to scalars. So I get an obvious map, which is the restriction map from V star to W star by just restricting to, forget that I could take inputs from V. Just remember the part of it that is only in W. Forget the rest of the inputs. Right? So moreover, the restriction map I'll call it res from V star to W star It just says literally take phi, a linear functional, and look at phi restricted to W. It still is a linear function from W to the field. The restriction map is linear. That's pretty much obvious. And I'll continue there. Linear and onto. So every functional in W star is covered. Okay, right from a functional can be extended to a functional V star. Linear and onto. And not only that, I can even tell you what the kernel is. The linear map has a kernel. The kernel is precisely the space that maps V star to 0, W that maps W to 0, namely that. So, in other words, I can therefore tell you a corollary, several corollaries. Corollary 1 is literally that W star is isomorphic to V star mod W perp. This is literally just by the first isomorphism theorem. And whenever you have a surjective linear map, the image is the quotient of the codomain of the domain divided by the kernel. And that's what we are saying. The image is the quotient of the domain divided by the kernel. And the second corollary is, what was the second one? If V is finite dimensional, then you can do the same thing. And then you know that the dimension of W plus the dimension of W perp equals the dimension of V. Why is that true? That is because what you know from the corollary 1 is that dimension of W star is dimension of V star minus dimension of W perp. So I can take the W perp on the other side and say dimension W star is dimension W perp is dimension V star. But if V is finite dimensional and so W is also finite dimensional, then W star and W have the same dimension. So this number doesn't change if you put a star. And V star and V have the same dimension, so this number doesn't change whether or not you put a star there. So therefore that's true. I just say from corollary 1 and dim V star equals dim V. And similarly for W. Right? And then there's a third corollary apparently. Yeah, I may as well say it. And that's basically this statement written in a different way. Okay, so I'll say suppose I have a corollary 3. Or an application really. It's really I mean I don't state a theorem here, I don't state a result here, I'll just state it. So suppose now I take a very specific V and W, right? So I take V is f to the n and A is f to the m cross n, right? And W is the kernel of A. Right? So this is again clearly the kernel of A is contained inside. A acts on f to the n, which is V, so the kernel of A is contained inside V. So it's a subspace, right? Now what is V star? This is column vector, so V star is f to the n transpose, right? Because it's f to the n star, which is f to the n transpose. We saw that last time, which is row vectors. Okay, and now what am I trying to say? What is W perp? Question is fine. We just wrote down what W is the kernel. What is W perp? Well, you can check. You can show. I'll just say I won't. I mean, this is not what I'll prove today. W perp is. I guess it is. So W perp is. So what is W? It's everything such that A times X is 0. W perp in V star is something which is something times A. So that something times A times X is AX equals 0. So it kills. Yeah. And so W perp is the row space of it. So anything times it. And now let us look again at this equation here. Or yeah, let's look at this equation here. Then corollary 2 says, I think that's basically it. Did I write down corollary 2 correctly here in my own notes? Yes. Now corollary 2 says, what is the dimension of W? W is the kernel, so it's the nullity. What is the dimension of W perp? W perp is the row space, which is the row rank, which is the column rank, which is the rank. And what is the dimension of V? It is n. So we get the rank nullity here as an application of this thing. Okay, so that's corollary 3, and now I think I should prove the theorem, I guess. So what was the theorem? Here is the theorem. The restriction map is linear and onto, and the kernel is precisely W perp, which I am erasing right now, the definition of W perp. Okay, great. So why is that true? Okay, so do I want to check linear and so on? No. Okay, first of all, the claim is that the restriction map takes V star to W star, so that's clear. So proof of theorem. Okay, so step A is that the restriction map does send V star to W star. That is clear, right? You take any map phi V star, implies phi restricted to W is linear on W. Right? If you know that phi of every element of W is an element of V. So if you take phi of CW plus W prime, then when W and W prime are in V, therefore phi of CW plus W prime, because it is linear on all of V, is indeed C phi of W plus phi of W prime. So it is indeed linear on W. And the value, everything in V went to a field element, so everything in W goes to a scalar, and therefore it's a linear map from W to a scalar to the scalars. Therefore, second is rest is linear. That is easy to check, so check yourselves. The part 3 is the part that rest is onto, and then the kernel. Well, actually, let's look at the kernel first, because the kernel is trivial. What is the kernel of this restriction map? It is the set of all linear maps in V star such that this map is 0. But this map is 0 just means phi of W is 0. So that's just trivial again. The kernel of rest, because W perp is just immediate, let's call it immediate, from definitions. So finally, you have to prove that the restriction map is onto. Okay, and so for this, I will start with. I guess we can just take a kernel basis of W perp and then continue. Or a basis of W and continue apparently. We can take a basis of W and continue. Fine. I want to say, okay, what do we want to prove? We want to prove that this is onto, meaning every linear map on V star, every linear map in W star can be a map from W to V can be extended to a map from V to F. Sorry, a map from W to F can be extended to a map from V to F. So let's start with the map from W to F and extend to V to F. For that, I start with the basis of W and extend to a basis of V. So here, did I say finite dimensional? Did my theorem involve finite dimension? I doubt it. Therefore, so let's say start with a basis. So I'm not saying it's a finite basis. I'm not even saying it's an order basis because it's not even a finite set. So I can't really order it unless I use something like the axiom of choice. But start with the basis wi, I in I, of w, extend by this set Vj, j in j, to a basis of V. Okay, and now given any linear functional in W star, I'm just going to define it in some different. I'm going to produce for you a functional in V star which restricts to W star, to that functional. Now, given let's say psi in or phi in W star, let's say psi in W star. Let me first make that notation change here. This should be psi. This should be psi tilde. Okay. Everywhere there is psi, of course. Okay, given psi W star, define psi tilde from V to F via the following. So I'm defining it and then I will prove it's linear, therefore it's in V star. I'm not already saying it's in V star, of course it is. So okay, define these things. How do you define it? So write down psi tilde of summation Ci Wi, I in I. Of course, this is a finite sum, so all but finite remaining terms are 0, plus summation Vj, Vj. Right? So because the Vj's and the Wi's together form a basis of V, every element of V is a linear combination of them. So I start with a typical linear combination, a general one. Of course, every vector is a unique such expression, and of course, it's a finite sum. So starting with such a sum, this I'm defining it. Basically, you can guess what to do. So for this part, I keep phi, and for all of this part, I just keep 0. This is defined to be psi. So it's psi of summation. I could do that, or I could do the other way, which is literally summation Ci psi of Wi. It's linear, right? So that's why I can say I in I. Define this thing, okay? Claim. Well, two claims. One is that psi tilde is in these. Psi tilde is linear hence in V star. And the second claim is psi tilde restricted to W is psi. This part is obvious, right? If you restrict a vector to W, how do you describe vectors in W in such a linear combination? Because this is a basis, all the Vj's must be 0, and whatever you have here is in W. But the moment this is in W, this is defined to be this, and this is just psi of summation Ci Wi, which is the original. So this is easy. Well, fine. I'll write down a formal proof of both of them, but I mean, it's really just writing down definitions. But let me show you how to write. So prove. First of all, let's prove 1. This is just obvious. It's linear because you can write it. So it's the same proof for both. So suppose V equals summation Ci Vi plus summation, Ci Wi, Vj Vj, and V prime equals summation. I'm not even writing down what these I and j go from. C prime I Wi plus summation j d prime j wj vj. And the understanding always is that all sums are finite, obviously. And alpha beta. I'm using C and D, so that we use alpha beta as scalars. Then, so this is like if you really write things down in definition. This is obvious. Both of these are obvious. I'm showing you how to formally write down proofs. And so then what you say that psi tilde of alpha v plus beta v prime. What is alpha v beta v prime? You have to regroup all of these things. It is psi tilde of summation alpha ci plus beta c prime I wi plus summation alpha di dj plus beta d prime j bj. You get the idea. It's literally just writing down tedious. It's a very tedious bookkeeping, but there is actually no intelligent, there's no subtlety. It's all exactly what it should be. Which is why I'm not even bothering to explain anything here, because there's nothing to explain. I'm just writing down exactly what it should be. Yeah, so now you write this down and you do the boring stuff. Okay, so now, first of all, by the definition, this is just this thing. This is equal to, you ignore all of these parts and you just write down the W's. So it is it is summation I and I. Psi of, and again, even here the scalar comes out. So alpha ci plus beta c prime I psi of wi. Okay. And now that I can regroup because these are all sums. This is summation alpha summation ci psi wi plus beta summation c prime I psi wi. And now this is equal to what is psi is linear, so I can say this is alpha psi of summation ci wi plus beta psi of summation c prime I wi. Oh, I don't need to do this again, sorry. Now, but on the other hand, let me, so this is the left hand side, right? Let me now look at psi of alpha, so let me look at alpha psi tilde of v plus beta psi tilde of beta. It's alpha psi tilde of v plus beta psi tilde of v prime. I want to show that this expression is equal to this expression. That is linearity. Well, what is this? I know this is alpha psi tilde of summation ci wi plus summation dj vj ij plus beta psi tilde of summation c prime I wi plus summation d prime j vj. And now again, you can use the definitions, and this is equal to alpha summation ci psi of wi plus beta summation dj psi of v. It's all very boring, but the point is now this expression is exactly this, and I did something wrong here. It should still be I. You discard all the j terms. That's c prime I wi. But this expression here is exactly the same as this expression here, and so the left hand side is the right hand side. I mean, so you get the psi tilde as it. And in exactly the same kind of boring, tedious bookkeeping fashion, you can prove that the restriction is indeed psi. Okay, it's just similarly tedious, and there is nothing, no novelty, no subtlety in this. There is no novelty, no complication. It's just completely straightforward that you restrict and you find it's the same thing. Nothing. Okay, so that's what it is. Okay, so that's the proof. Fine. Sorry, where was this? Here. Okay, so now finally, so that ends so the Perp-space result is done. I'm just telling you a bunch of different things you encounter in linear algebra, dual spaces, Perp-spaces, and now we get to the next thing we encounter, which is the double zero. Pretty much exactly on time. So. Okay, so first of all, the definition is straightforward. But for every vector space, you have a dual space, and we said that the dual space of a vector space is a vector space. So it has a dual. So V to V star to V star star. That's there's nothing I mean, nothing. There's nothing new in this. Okay. So, for example, if V was Fn, then we know that V star is Fn star, which is isomorphic to Fn transpose. And then I could say that V star star, is it isomorphic to Fn transpose transpose? Which is just transpose transpose is just Fn itself, which is V. So is it true that this is the case? The double dual is exactly the same as the original space? The answer is yes, if the original space is finite dimensional. Otherwise, the dual is bigger and the double dual is even bigger. Okay, so you can check. Okay, so what happens in general? Okay, so that is one thing. Okay. We will prove this. We will say something about this right now. Now, the next thing is I want to give examples of elements in the double dual. Let's call this a map in V star star. Example of what? Example of elements in the element E is an element, if you will, in V star star. The idea is the following. Let's see. I can use this now. The idea is the following. So suppose I take a vector V in V. From this, I'm going to describe for you the map EV in V star star. EV is for evaluate. So I'm going to define this thing is defined via so it has to take an element phi in V star. Let me put the phi underneath. And evaluate means you can guess what this is going to do. It's going to give you the scalar, which is phi. And the claim is this is exactly a linear functional on the dual space. Okay? So check this is linear on V star. And therefore it's V star star, right? That is the claim. That is not hard to check. So fine. And now comes the theorem. That means what does it mean? It means you get a map of sets, right? So we get E, which goes from V to V star star. V goes to EV. Map of sets. And it's a map of sets, but it is between two vector spaces. So of course, in the category theory spirit, it would be nice if that map was actually a morphism in that category. And the answer is absolutely yes, it is. Theorem. Right. The map E sending V to EV is indeed a linear map. It is, I think, 1-to-1. Yeah. Let's not call it E, it might be confusing. I'll call it capital phi, because, well, also because that's what I wrote in my notes. The map phi from V to V star star. So this is part 1. The map phi is linear and 1-to-1. Okay? And the second part is if V is finite dimensional, then the map is onto, and therefore an isomorphism. and phi is also onto. Okay? Think that's it. Okay, so let's check this. Again, I will probably not check that phi is linear. So you can do that. I mean, that's obvious. That evaluated v plus evaluated v prime is the same as evaluated v plus v prime because all the maps in the domain are linear. Proof. In part 1, A. So I proved in part 1, A capital phi is linear. I will leave it to you guys to check. Okay, now part B in part 1 is to check that it is 1 to 1. That is what we need to check. That is also not too hard. Why? So look at, let's say an element of V. So let's say V belongs to kernel of capital phi. What does that mean? It means that every element of V star is 0, right? So every element of V star evaluated at V is 0. I.e. EV of phi, this phi of V is 0 for all phi in V star. Sorry, 1 second. Oops. Phi in V star is 0. And now how do you prove that V has to be 0? So here is what you do. Here again, I haven't said it's finite dimensional yet. So I have to use Zorn's lemma, but I extend V to a basis of capital V, of the vector space. And using that, I cleverly define a linear function. Just getting destroyed. Okay. Now extend V to a basis. How do I say this? Extend V via using Bj, J in J to a basis of V. And define, I'm going to define a new functional, but I'm going to define a function, I'll define a function phi from V to F via phi naught. Phi naught of, let's say, C times V plus summation, or let's say B times V plus summation Bj times Vj. Right? So any element of V is a linear combination of the original vector V, which is non-zero. I should have said that V is non-zero. So if V is non-zero, we want to prove that V is 0. Right? The kernel is, we want to say it's 1 to 1, so the only vector that's in the kernel is 0. So clearly 0 is in the kernel, but suppose some non-zero vector is in the kernel. So if V not equals 0, extend. Then extend V to a basis. Let's say V is a linearly independent set, it can be extended to a basis. That is part of Zorn's lemma and this. And so dV, blah, 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 fine. So this thing is defined to be D, actually this D. The claim is this is a linear function. So claim phi is phi naught linear. And you can again check. Okay, it's a function from V to F clearly. You just have to check it's linear. And of course, as always, I will not check it's linear. But now you get a contradiction. So you assume that V is non-zero and in the kernel, then I claim this is a contradiction because what you get, you know that this is true. In particular, phi naught of V is 0. So on the one hand, you get 0 equals phi naught of V. But on the other hand, what is phi naught of 1 times V plus anything plus 0 times the rest? It is 1. And so I get 0 equals 1 in the field, which is a contradiction. So the assumption that V is non-zero must be false, and therefore V is 0. But V was any vector in the kernel, which means the kernel is 0, which means that map phi is not true. Because that's not too hard. The second point is interesting. Suppose V is finite dimensional, then phi is actually onto. And that actually we have already done in some sense. How do you do this? Well, you know the map is 1 to 1. If it is finite dimensional, then V star and V have the same dimension. But now V star is finite dimensional, so V star star and V star have the same dimension. So which means V star star and V have the same dimension. And here is a linear map that goes from one vector space to another with the same dimension and is 1 to 1. As a consequence of the rank nullity theorem, we have proved that any such map must also be onto, so we are done. Okay, so I think that was that. Yeah. So where do I write this? Maybe I'll start writing it here. Part 2. If dim V less than infinity, then V star equals dim V less than infinity. We have already proved this. This then is by class. So also dim V star star is dim V star with a 1, which is 1 star, but was equal to dim V. And that is less than infinity. And now because these two are equal equidimensional spaces and phi is linear between them, since moreover, since phi is linear and 1 to 1 from V to V star star, it is also onto, it must be onto by a corollary of the rank nullity theorem we saw in class. That makes sense. Okay, great. So that is that. And now finally, having done double duals, this result of double duals, I can come back to the transpose and the matrix of the transpose with respect to the dual basis, the adjoint to the transpose. Right? So let's come to that. I need some water. Okay. A second. Okay, so now we come to the double dual again, sorry, to the transpose again. Maybe I can use blue pens. Okay, so back to transpose. I mean, the point is, everything here, what I'm going to say, could have been said without talking about double duals. I won't even talk about Perp-spaces, but double duals I could have avoided. Except at one place in the proof, you need double duals. So that's why we have to sort of start with double duals and then go on. Okay, so now I can explain to you. So recall at the beginning of the lecture, the thing I did not erase, right? So recall from last time basically, and from the beginning of the board this time, recall given vector spaces, let's say given T in Lin, F, V, and W, which automatically clarifies that V and W are F linear vector spaces, T is a linear map between them, and there was this, we defined T star in Lin, F, W star, and V star. Okay. So now the question is, what are the, so now let's say, or maybe should I just write down the theorem first? Yeah, I can just write it as a theorem. No, let's just put in notation and then say with the above notation. Okay. Now fix bases, a fixed ordered basis. Sorry, because we are writing down a matrix. So you have to order them so that the rows and the columns are fixed. Fixed order bases. So first I'll write down bases of V and W. Then with respect to that, I will write down dual bases of V star and W star. So let's say V equals V1, Vn of V, and Vw equals W1, Wn of W. Okay, and with respect to these, I define the dual bases. V star equals phi1, phi n of V star, and W star, let's call this psi1, psi m of W star. Okay, then I have two different matrices. There is the matrix of T with respect to these two bases, and there is the matrix of T star with respect to these two bases. The question is, how are these two matrices related? That is the point of the next result. As I said, so far I don't really need double duals, which I have been telling you about. I do need them in just a minute in the proof of the result, but not in the statement of the result. So yeah, I can state the theorem now. Theorem, I can state it here. Is this legible? Yeah, reasonably so. With the above notation, it's getting bad. The matrix of T star goes from W star to V star. So I have to first write down B star and then B W star equals, I take the matrix of T with BW, BV, and I simply take the transpose. That is the theorem. So it's just all of this notation fits together in a transposey way. That's really what it is. Okay, that is the theorem. The proof is, okay, the proof, as I said, is this you might think again is another straightforward, boring, subtle, unsubtle proof. In some sense it is, but there is a small subtlety that you should use double duals, basically. Okay, so I'll tell you how. Okay, so let's give the matrices names. So the proof, denote, let's call this maybe, I won't use B because B stands for basis. Let's denote A to be this matrix. This is an M cross N matrix as usual. And C equals this other, the left hand side, which is, I guess, N cross N. Okay, great. So now first, I want to compare Aij and Cji and say that they are equal, right? So what is Aij? No. So given any matrix and so forth. Aij so I keep saying Ji because when it is this way 1 less equals I, sorry. But the moment I say Ji and not Ij, I can then say that so that 1 less equals I, less equals M, and 1 less equals J, less equals N. Then Cji goes from N cross N matrix, and Aij is M cross N matrix. That's one. Okay. So now let's look at Aij. On the one hand, it is what is it? It's literally Ei transpose A times Ej, right? That's what it is. And similarly, Cji is Ej transpose C times Ei. But then what does that mean? This is a matrix, but this means what is this EJ? All of this is with respect to BW and BV. The whole point is these are not just entries in the matrix. They stand for a linear algebra phenomenon without using, including using basis vectors, not the coordinates. This really means, what is EI transpose? So EI transpose is EI star with respect to the basis of W. Or because you're taking stars, you should be taking the dual basis, right? It is the dual basis to the EI vector times A, which is the matrix of T with respect to BW and BV, times the EJ with respect to BV. Okay, great. That is what it is. Now, what is this? The EI transpose equals EI star. Well, what is the dual basis to EI? Well, what was EI? EI is WI. So EI here, with respect to the basis BW, is precisely WI. With respect to BW. So with respect to BW, what is the dual basis to WI? It is precisely psi I. So this is psi I of, this is just, okay, now what is TBW times TVJ? It is exactly T of EJ, T of whatever this vector is. But what is this vector? It is again VJ. So it is T of VJ. You get a scalar here. This scalar is by definition that, or that thing by definition is this scalar. Okay, great. This is what this is. What about CJI? Similarly, this is what happens on the AIJ side. Let us similarly compute CJI and check that they are equal. And if I can prove they are equal, then that is exactly the transpose. Similarly, and now that is where the fun begins. So far I have not used the double duals. So far I can do all of this at the beginning of today's class. I need not have told you anything. You use dual bases, but that was already done last time. So far I have not used, okay, double duals. But now let's look at similarly. CJI is EI star, EJ star, T star, T star in the, I need to give space for the, what do you call it? This should be square brackets, of course. All of these are square brackets because they have coordinates with respect to some bases. EI, sorry, my mistake. But now you see the matrix C is between dual spaces. So let me first write down this is BV star, BW star. So therefore this is BW star. And this is itself BV star. Okay, so what does this mean? This is the dual basis to BV star, or the jth dual basis vector. But what is the dual basis of this thing? That is what we have to compute. So here is where I take a short break from this proof and we answer first of all the question, what is the dual basis to this dual basis to the basis Vn? You start with the basis V1, V2, Vn or V. From there you get this basis of V star. I want the dual basis to this basis. And that is, I guess, maybe your next homework problem. It's a trivial verification. You just have to verify that it's a basis. And you have to verify that the evaluation is delta ij. But let me give you that homework problem. Homework. Maybe I should put this in black because it's not part of the proof. What is this? And that is answered by the homework problem. Say VV equals V1, Vn is ordered basis of V, ordered basis of a finite dimensional F vector space V. Okay, and maybe I'll put a comma here, and V star equals psi 1, psi n is its dual basis. So psi I of Vj is delta ij. Then now here is where you remember what I told you about double duals. I gave you an example for double dual, the capital E, evaluation vectors. Then if I write down this ordered collection of vectors, linear functionals, EV1, EV2, EVN. So the VIs are these vectors, is the dual basis to VV star. So this is the dual basis, the evaluation vectors. That is the homework problem for this next homework 8. Using this, I continue back to the fifth. So now let's come back to this calculation. I already told you that let's say, I will comparing these two matrices that I just erased. Let's denote A to be the right-hand side matrix without the transpose and C to be the left-hand matrix, right? So I've calculated the entries of the right-hand side matrix A over here. It is this psi of T. I want to calculate similarly the entries of the left-hand side matrix. And what I said was we have, by the same token, I want the JF dual basis vector to the VV star here. Well, now I know what the JF dual basis vector is, so I continue. So continuing. Using this homework problem, this is equal to, what is the JF vector? It is E Vj. Evaluated at, similar to that, it is T star of the ith basis with respect to W star. But what is W star? It was, I erased this, it was psi 1, psi 2, psi n. So the ith basis vector Ei corresponds to psi I. So it is T star psi I. That's exactly what this is. Okay? That's by the definitions. But now EVJ means evaluation, so let's evaluate this. So this is this thing, T star psi I, evaluated at Vj. And now you have to remember what is the definition of T star, the transpose map. What did this mean? T star of psi is just post-composing, right? Post-composition. This is literally equal by definition to psi I of T of Vj. And so guess what? This is exactly Aij. So we saw Cji equals Aij, which we see as A transpose. So it's just a matter of following the definitions down, except you have to remember that there is a double dual involved, and the dual basis to the dual basis is basically the original basis as far as evaluating goes. Okay, that's what that is. Okay, so with that we actually come to the end of the chapter on vector space, abstract vector, of this part of the course on abstract vector spaces. And so the next thing I want to do is determinants. So today we won't go to the full determinant class. We will just talk about something which is still abstract vector spaces, namely multilinear maps. Okay, so we have talked about single linear maps everywhere. Linear maps are everywhere. We've talked about bilinear maps when it came to defining the tensor product. So today I'll just do multilinear maps a little bit, maybe not too much, and we will stop slightly earlier than normal. And then on Thursday, we will talk about the determinant function and alternating maps and how do this. Yeah, we will get there. But yes, in some sense, yeah. So morally, this already ends the chapter on abstract vector spaces and abstract morphisms and so on. But we will still talk about multilinear maps. So morally, you could say this is still a continuation and so on. Okay, but yeah. The aim is to go towards determinants, and on Thursday we will. Okay, let's see. So, yeah, as I said, we've already seen. Oops. Already seen linear maps and bilinear maps. Linear maps from V to to W, and bilinear maps. Now we shall define multilinear maps. I may as well just define it, I guess. Yeah, more generally. We've also seen how to take Cartesian products of 1, 2, finite, arbitrary sets of vectors. I'll just take a finite multilinear map. More generally, definition. Maybe two definitions, I guess, and to denote the space of multilinear maps also. Yeah. So given F vector spaces, V1, V2, Vn, and W, a function, a map, I guess, a map T from V1 cross V2 cross Vn to W is multilinear, F multilinear, but I mean fine. If for all you can guess what it is. It's linear in every coordinate. Right? There's nothing more to say. If for all choices. Let's see. So for all. Maybe I'll write down the condition first, and then I will write down the quantifiers. So if T of, so you fix V1, you fix V2, you fix Vi minus 1, and then you write down Cv plus C prime V prime in the ith position. Again, Vi plus 1, Vi plus 2 till Vn. So you fix all positions except the ith one. This should obviously equal, it should be linear in that. So C plus C prime T of V1, Vi minus 1, D, Vi plus 1, Vn, plus C prime T of the same thing with V prime in the ith position. Vi minus 1, V prime, Vi plus 1, Vn. And now I write down the quantifiers for all Vj in Vj for j not equals I, and V prime in Vi, C prime in F. This is the definition of the multilinear map. It's just a mouthful, but the point is it is extremely obvious what it is. It's just that one has to write it carefully. That's why we take so much time. Okay, so now, and then of course we denote this, like we said lin and bilin, we write multilin. Denote the space of such maps. Okay? All such maps. Okay, great. So now, theorem, lemma. It's really a lemma, it's really nothing. But this is a vector space. And because these are all maps, that means they're all functions, right? So it's a vector space under the same things, under pointwise addition and pointwise scalar multiplication. So multilin, I should probably say for all vector spaces and so on. So for all n bigger equals 1, fields F and F vector spaces, V1 through Vn and W, the set multilin of V1 plus V2 plus Vn, and W is an F vector space. Let me just say here under pointwise operations. So the negative is pointwise, the addition is pointwise, and I think this is already not just a lemma but also a homework. So let's call it a homework lemma. Fine. It's really nothing to check, but fine. Now this is the first course officially in linear algebra, so you have to do the boring stuff as well. Okay, fine. Let me give you some examples, and I guess that's pretty much the end of the class. One example is obvious. The map that takes everything to 0 is clearly multilinear. 0 equals c times 0 plus c times 0. C prime. Okay. Let's do a different one. So let's say v1 equals v2 equals vn. In fact, this is what we will assume for everything beyond this point. Okay? And W equals F. We will always assume from now on that all the input spaces are the same and the output space is the same. Okay? Maybe I don't really need this right now. Let me start by just assuming that first and then we will get henceforth. Okay, so now with the setting example to say equals V, let's say, okay? And W is a scalar. So say V has an ordered basis. Actually, I want the ordered basis to also have size n, the same size. Okay? But right now, let's say V1, V2, Vk. It could even be infinite, I don't care, but fine. Okay? And define. So I need to define the multilinear map. So define T of, let's say C11 V1 plus summation C1 J Vj. J bigger equals 2, and then C21 V1 plus this. Every vector in V can be written as a combination, right? So that's what I'm doing. C2J Vj and so on till Cn1 V1 and so on. To be equal to C11 times C21 times dot dot times Cn1. So clearly this is an element of W, which is the scalars, and clearly all of them have the same basis because they are all the same vector space. The claim is that this is a multilinear map. And you can check, that's obvious, right? So for example, if in the first coordinate you had C11 equals this thing, time plus D11 V1 plus something, right? Then you would write C11 plus D11 V1 plus the rest of it. So this would just become C11 plus D11 times the same things here. But that is equal to C11 times all of this plus D11 times all of this by the associativity in fields. And so indeed that is equal to this plus this. So you can check for yourselves, check this is multilinear. So you can say alpha times this plus beta times that, but what you will basically get is alpha C11 plus beta, let's say D11 times C21 times C31 or Cn. And that is indeed equal to, so the left hand side here and the right hand side there. Actually, that is indeed equal to, so you would have to check basically that the left hand side, if you took a linear combination, the left hand side would equal this thing, but on the other hand, this is alpha times C11, C21, dot dot Cn1 plus beta times D11 times C21, Cn1, and that is equal to dot 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 equals the right hand side. That is how you would check that something is multilinear. Okay. That is the second example. Now let me do one last example where I specialize even more. I am going to take two-dimensional vector space, F2. Not just any one, but F2. Okay, so now let me take n equals 2 and v1 equals to v equals 0. And now you see that the basis has size k equals 2 again as well. So all n, k, v1, everything is F2 and 2. Okay, so now I have column vectors and now I define. I'm going to give you 3 examples of maps. T of AB, this is one vector, and CD, this is another vector. So the example that I gave here is this the V1, so it's A times C. But similarly, I could have taken the second coefficient, I could have done B times D. I could even have done A times D or B times C. All of these are all linear, are all multilinear. Well, for n equals 2, it's just bilinear because bi is 2. But yeah, they're all multilinear maps. That's very interesting, isn't it? Right? But now you see, because this thing is a vector space, I can take linear combinations of these maps, and those are also multilinear maps. So you can check. This is you have to check. So check they are all multilinear. But therefore, hence by the lemma, is an F vector space. This thing here. Right? Let me put it slightly better. Let me take it all the way here, from here. So hence by the lemma, the map T of AB, let's call it T D of AB. Oops, I can't call it D because D is here. Let's call it, I'll just call it T naught. AB comma CD. I can take a linear combination. Let me take 1 times this and minus 1 times this. This is a multilinear map. So you've seen bilinear maps, linear maps, multilinear maps, and this is an example of a multilinear map. Of course, it's a very, very special multilinear map. That is fair. So from next time, we will talk about such maps, except we will no longer talk about separate columns like this. We will just say, look at the entire matrix and call T naught of the matrix ACBD to be this thing. Then this is multilinear map as a function of the columns, but we will just look at it as a function of the matrix itself. That is the starting point next time. So I'll keep this example, I won't erase it. Next time I'll start with functions of matrices. And those are basically going to be special functions which are multilinear in the columns of the matrix. And this function, of course, is very, very special. This is where we are getting to. This is called the determinant of the matrix A, B, C, D, or ACBD. Yeah, so we will get there next time. So today we stop early, about 15 minutes early or something. Yeah. So I'll just go this way if you want to see the last. Yeah.